All right. Hello, everybody. I just wanted to go through some information for probabilities, right? Using our classical calculation, our classical formula for doing those calculations, setting up those problems. Likewise, going through some examples dealing with our two-way classification, which was a common example and a common practice that we see in statistics calculating probabilities. And so in that discussion, we'll see kind of setting up that classical probability formulation and also some steps that I might use to kind of bypass or not use the formal calculations for the and the or statements, the multiplication rule, the addition rule, and so on, are kind of building those in these calculations. Okay, so I wanted to kind of show. I'll do some notes here on the second screen, and then also go through some practice problems in C mode. Okay, so here we go. Here's my set of notes we'll go through, right? But definitely, as we're looking at our kind of classical or traditional probability formula, this calculation, right? When we're asked to find the probability of some event, some outcome, right? Our probability of that event E, or probability of that event A, whatever we decide to call it, right? When we do that calculation, we build this formula, this fraction, this ratio, right? This division, where we're looking at in the numerator the number of outcomes, right, that satisfy that event E, right? So basically in that numerator, we're counting up the number of ways that we can get that event E, whatever it is, right? When we're rolling a die, the probability of getting an even number. When we're flipping a coin, the probability of getting heads, right? Or when we have like a big group of students, the probability that in that group of college students, that the student I select, that their major is math, right? Okay. And so in the denominator, this is our total number of possible outcomes. And really here we start to see some of that phrasing again, right? This is kind of our n, right? This is our size of the sample space, right? All those possible outcomes, n or capital N, right? That's our number of possible outcomes we get for that experiment that we're running, right? How many students we have to pick from, how many objects we have in a box to pick from, right? Or in terms of like flipping a coin, as simple as that, how many outcomes there are, just two. Either we flip a coin and get a heads, or flip a coin and get a tails. Some other outcomes that we'll see, rolling a die, a common six-sided die, the results 1, 2, 3, 4, 5, or 6. Drawing a card, that business. But when we start to set up our classical probability formulation, number of outcomes, number of ways we can get that particular result E, divided by the total possible number of outcomes. Okay. As with that said, one common way where we start to see this formula being used, right, is with our two-way classification table. So here's some notes I have produced. And again, we can find these online for us to look at as well. Okay. I can zoom in here a little bit. Get that to work. Okay. But looking at this table, right, we see this information, our data, these information about college students, right? And the information regarding their transfer level math course that they're taking. And so we have two ways of classifying what year in college they are, like freshmen, their first year in college, sophomore, their second year in college, our community college system, right? Commonly 2 years. And then the other way of classifying which class they're particularly taking, our stats class, stats T1000, pre-calculus math 13, or our calculus, first semester calculus math 28. And so we look at this data, we have all these different students that we've taken this information from. And so one thing before we get into the calculations is just figuring out, right, how many students, how many values are in each of these different groupings. So if I take the sum across that top row, figure out all these freshman students, if we do this quick addition, you can kind of see that calculation, 124 plus 82 plus 36 pressing enter here. For the total number of freshmen, 242. Then for the number of sophomores, we can do 148 plus 64 plus 42. I have 254 sophomores, right? So kind of a decent balance between the number of students from each year in college. We'll also want to figure out the different classifications, how many students we're taking statistics, 124 plus 148, 272 there. That written. The next one we have here for Math 13 pre-calculus, 82 plus 64, 146. And then now lastly, number of college students taking calculus, Math 20A, adding those up, 78. Okay, and again, that's just for this particular sample. Thinking about having a simple random sample so we get a good distribution from our entire population. But now we can start to identify, right? So for this top row, all the freshman students that we have in our sample, there are 242 freshmen, 254 sophomore, second year or above students, and then also the different categories of which math class they're taking. And so if I add those quantities together, so just adding up the total number of freshmen and sophomore, 242 plus 254, we get this total 496. Likewise, right? So again, putting this classification of which you're in college you're in, we're getting 496 total. It should be the same as we start to identify which particular math class they're taking, 272 plus 146 plus 78, 496 again, right? So in this case, this is our sample size. This is our N, that total number of students we're going to be drawing from, right? So now thinking about that calculation for our probabilities, when we start to think about these different categories, the probability that when we pick a student that we're going to get in this first problem, right, a sophomore, we have our number of sophomores out of that total group, that sample size, right? So there's kind of that first step, even this first problem, seeing how we're going to build up that fraction. And when it comes into our calculations, right, kind of showing our work, thinking about how we're evaluating, right, we want to see that fraction that we're using to compute. So in this case, if one student is selected at random from that sample, what is the probability that the student is a sophomore, right? So for some notation here, we can say, okay, we're going to take this probability, and then our event, our outcome we're looking for is that student we pick is a sophomore. So there was like our event E or A or whatever label we want to give it. And so now the probability of getting a sophomore, though, we build our fraction, the number of sophomores, 254, divided by the total number of students that we're drawing from, that 496. And if we do that division, right, so there's our fraction, we could simplify that fraction. They're both even, so I know I can divide by 2. We can check for other factors that might work, try to divide by 4, 8, so on, okay? But if we go into our decimal work, if I take that 254 divided by 496, doing that calculation, the long decimal, so my unrounded decimal solution, 0.5120967774. And with probabilities, kind of setting us up for future work and common practice, I'm going to round this probability to 4 decimal places. So if I round to 4 decimal places, then for our result here, and I get one more color to show up here, rounding to 4 decimal places, 1, 2, 3, 4. Looking next door, that 9 says we round that value up. And so as my rounded value, my final probability solution, 0.512, now that 9 rounds the 0 up, so we get a 1 there. Right, so there's our probability. And when we're doing the calculations, showing that fraction we're using to calculate the unrounded decimal solution, right? Keeping all those decimals from our calculator, or likewise, if we're using decimals, calculations, whatever it might be online, so on. And then our rounded value, typically for decimal places for probabilities. And so now if we start to look forward, now if one student is selected at random from the sample, what's the probability that the student was a freshman and was enrolled in Math 13? So now this brings up one of those key phrases, those key terms. We have our and. And so with that word and, mathematically, this is what we would call our intersection. That's spelling, right? The intersection. So exactly that, we want to see where do those rows, where do those columns, this information overlap, right? Because with that word and, we want to be both, right? That result, that person we pick needs to be both, needs to satisfy both, right? That freshman and in Math 13. So as we start to build up this probability problem, we're taking this probability that that student we select is a freshman, kind of getting those colors to coordinate, and that particular phrasing there to be in Math 13, our pre-calculus class here. And so, as I mentioned earlier, briefly, there is a formal multiplication rule, a formula that we can apply with our probability calculations. But truthfully, especially when we have this kind of information laid out, I'm kind of bring this down a little bit to zoom in manually here, okay? What we start to see is that, well, instead of kind of going through that longer formula, thinking about this fact, okay, we're looking for the intersection, the overlap with that word and, thinking about these students out of the 496 that are both freshmen and taking Math 13, okay? Looking at our table, well, in that denominator, let's start off with that. We know there's 496 students that we're going to pick from. So from that group, how many are both a freshman and taking Math 13, right? Thinking about where this row, this column intersect, that overlap, that one set of students that are both freshmen in that row, in this column for Math 13, there's 82, right? So in that grouping, we have 82 out of that 496. And now there's our fraction to calculate. So we can do the long decimal calculation, 82 divided by that same 496. The long decimal unrounded, 0.16532258 And then as our typical practice, rounding to 4 decimal places, 1, 2, 3, 4. That 2 says that that value in our 4th decimal place can stay the same. So as a rounded value, I'll put that right here, 0.1653. There's that rounded result, right? So that probability, the chance that when we do take that group of 496 students, the probability that we get a student that's a freshman, right, or their first year in college, and taking pre-calculus Math 13, our probability is 0.1653. If we start to do those kind of interpretations, that we have a 16.5% chance of that happening, right? Or about 16.53% of this sample has that characteristic as we start to look, right? For our calculations, though, see what we have here. So now as we go forward, thinking about some of these other possibilities, next problem, if one student is selected at random from the sample, was a probability that the student is a sophomore or was enrolled in STAT C1000, right? So that or, now we're a little bit more lenient, right? We're more inclusive because now or is our union mathematically, okay? And in this case, kind of sneaking down to this line, basically with that union, that or statement, right? Our result can be either, okay? It doesn't have to be one only, it could be both together or just one alone. And so when we look at that probability that the student we pick is a sophomore or taking that stat class, won't build up this fraction, this calculation, still taking from the entire sample, that 496, what we can do, right, kind of following along with that process in our formulas, we can take that total number of sophomores, 254, or goes along with an addition, being stat C1000, that 272. But now we have to be careful with these or statements, these inclusive, because we want to make sure we don't have double count. We don't want to include more values than are actually present. And if I was to add these two values, I'd get a total bigger than 496. I'd have more students that satisfy these than are even in the sample, which is impossible, right? How am I going to have more than what I started with? And so with these or type problems, what we have to watch out for, what we're going to see with our subtraction, kind of like we see up with our and, we see that we're double counting because there's both sophomores that are taking stat C1000. So they're included in both that 254, that 272. So to make sure it's only included once, we need to subtract off that duplication, subtract off that intersection, and we can do that calculation. Okay. Similarly, out of that 496, if I work from my table, now this is where we can kind of take a little bit of shortcut or be more direct. From our table, taking those values that are either sophomore or taking stat C1000, we can start to do that build up again, right? There's 148, 64, plus 42, those students that are sophomores, but then also add this other value in that stat C1000, that 124. So here's our sophomores, here's those extra freshmen that are taking stats. And those two quantities should give us the same result, okay? And so I know I'm kind of running out of space here, but if I do that calculation, or like what I can share the screen for the Desmos calculation, but if I was to do this calculation, the 148 plus 64 plus 42 plus 124, that total 378, okay? Let me sneak up here, 378. And if I do the other version, 254 plus 272 minus 148, make sure I type that properly. Notice we get the same 378. So either way we look at that problem, that kind of more formal and statement, the additional for probabilities, okay? We have outcomes, events that are not mutually exclusive, watching out for that overlap. Or if we take our values from our table directly, making sure we don't miss out any or double count, we get that same total. And so we do that calculation, 378 divided by 496. 378 divided by 496, 0.7620967774. Okay. And again, I'm running out a little bit of space, so I'm going to do my rounding right away. I would definitely ask for that long decimal answer on our work, but for now, 0.762. And now in our fourth decimal place, that 0, the 9 rounds us up, similar to our first example. So that would be my rounded decimal solution for this problem. Okay. And so then in this case, we had that subtraction going on. Let's see what happens with this next problem has an or. If one student is selected at random from the sample, what's the probability that the student enrolled is in Math 13 or Math 20A? All right, so again, we have that or, we have that union, that student can be in either one of those two classes. But what we notice in this case, what the important aspect is here, is that in this particular pair, Math 13, Math 20A, in this case, we start to see that these are mutually exclusive. That we can't have a student that's in both Math 13, Math 20A, that there's no overlap, there's no intersection. So in this case, when we start to look at this probability, that when we pick a student at random, that they're in Math 13 or Math 20A, right? These two separate columns in our table. When we do that calculation, again, we're still taking it out of the total, 496 students sampled. Those number of students in Math 13 pre-calculus, 146. Or Math 20A, 78 students there. But notice, there's no place where these columns overlap. If we were to bring in that quantity, that overlap intersection, minus 0, right? There's nothing to take away because they're all separated. And so we do that calculation, 146 plus 78, we get 224. And that's where I would mention again, if we were to do this freehand, right, without that formula, take those values from Math 13, those from 20A, and we get that total 224. Still taking out of the entire group, 496. And if we do that division, you kind of see that over here, 224 divided by 496, that may be better about writing that long decimal solution, 0.45, 161, 2903, rounding to 4 decimal places, 1, 2, 3, 4, that's 6. The one next door to the right, 1, lets that value stay the same, right? When it's 5 or bigger in that value to the right, we round up, we bring that digit up by 1 unit. 4 or below, 4, 3, 2, 1, 0, that digit stays the same. So as our rounded value, 0.4516. There's my rounded probability for picking a student that's either Math 13 or Math 20. So this last problem, again, a kind of special phrasing here, if one student is selected at random from that sample, what's the probability the student was enrolled in Math 20A, given that the student was a sophomore, right? So when we're using this phrase given, this is our conditional probability. We have this condition, this event, this statement that we are known, that is known at the start of the problem. In this case, what we start to see with our conditional probabilities, these given type statements, is that now we know our selection already satisfies an event, right? An outcome, a characteristic. So in this case, as we start to see, we're taking this probability that when we pick a student at random, that the student was enrolled in Math 20A. And now that given, mathematically in our symbols, we use this kind of vertical line. That's the given, that's that phrase. And then now that student was a sophomore. And so when we look at these problems, when we have a given type situation, probability of A given B, right? That second condition, whatever we were given, that's the event, that's the characteristic that we already know is satisfied. So in this case, we know the student is a sophomore. So instead of having to draw from that entire 496, now we're only selecting from the sophomores that 254, right? So this limits, it reduces, right, the denominator. We know that that student being selected is from the sophomores. And so even when we're looking at our table, I'm only going to consider those students in that sophomore grouping. I can forget about the freshmen And so now from that sophomore group, how many were taking Math 20A? Make sure I get the appropriate class. Math 20A was 42 of those sophomores, right? So I'm going to put it in the numerator, 42 of those sophomores out of 254. And so then we do that calculation, 42 divided by 254, right? We get this long decimal 0.165354331. Rounding that to 4 decimal places, that 5 rounds us up, right? So as a rounded result, 0.1654 now. Right, so using that two-way classification table, seeing some of those kind of special phrases or special wording, and, or when we have an overlap, when there's no overlap, intersection or no intersection. Okay, and then likewise with our conditional probabilities, some of those calculations. And we could use the more formal formulas that describe in the text, as we'll see online, and so on. But truthfully, especially when we have the data kind of presented to us directly in this format, it might be easier just to do those values taken directly from the table to calculate, to set up that fraction first in how we're calculating, get those long decimals, and then the rounded values, right? Again, typically 4 decimal places. Watch out online in some of the online homeworks. They ask us to round to different place values, but commonly, when I ask you to be for 4, okay? All right, so now we have those types of probabilities. Another type of probability that we start to see once we get away from having those smaller groups, okay, and we'll come back to that type as well. But I also want to identify this kind of probability of making selections, all right? And so in this case, looking at these problems, when we're given this data about like a recent poll finds that 46% of consumers, right, when we're given these values for a population, for a large group as a percent, now what we start to see is that these percents commonly represent our probability now, right, for making these selections. Because if we have a large population we're picking from, right, all the consumers that are buying peanut butter, okay, that like peanut butter, right, that's a huge population, like millions of people. So instead of having to count individually, now we can start to take this data, and so now when we're making selections and so on, when we're given as population, the probability is not decreasing, as we'll see in this next example, okay? And so then in this case, what's the probability that a randomly selected person will prefer chunky peanut butter? There's my probability, right? So for our probability that this person prefers chunky peanut butter, I'm going to go PB for short for peanut butter, okay? Just save myself some writing. The probability that 46%, converting that to a decimal, right? You take the decimal point where it's visible. If you don't see one, it's at the far right. You move it 2 places over. As a decimal, it's going to be 0.46, right? So in our calculations with probabilities, we're going to use decimal values or fractions, right? 46%, 46 over 100. And we're going to use those to evaluate. So then, what's the probability that a randomly selected person will prefer smooth peanut butter, right? Assuming that there's only 2 options, like kind of like heads and tails, right? Or we could have also said, what's the probability that they will not prefer chunky peanut butter? So in this case, this smooth peanut butter, this idea, this is our complement, right? This is our A bar, right? Or that complement, a little C exponent, or it could be event E, whatever you want to call it. There's our complement. And so we're using this key fact that when we're looking for the probability of the complement, I'm going to use A bar for my notation. that smooth peanut butter, right? We're going to do 1 minus the probability of the original, right? Because these kind of balance each other out. 1 is our total number of possible outcomes. So this complement, right? All those outcomes that don't satisfy the other. So we do that 1 minus to get that total. So in this case, if we're looking for the probability that this person prefers smooth peanut butter, we can find that quantity out by taking 1 minus the probability that that person prefers chunky peanut butter. All right, so we're calculating here 1 minus, I'll go into red here, 0.46 at 46%. So that probability, doing that subtraction, 1 minus 0.46 or 100% minus 46%, what we're going to get here, 0.54, right? 54% prefer that smooth peanut butter. So now, what's the probability that when I randomly pick 3 people, that all 3 people prefer that chunky peanut butter, right? So in this case, watching out, we're going to pick 3 people, right? And we want to see that all 3 people prefer chunky peanut butter. And so we start to see this kind of tying back into our statements with and or and whatnot before. Well, we can start to see that, well, in this calculation, I want to see that this first person I pick, right? Person 1 prefers that chunky peanut butter. And person 2, that second person we pick, prefers chunky peanut butter. And that third person, person 3, also prefers that chunky peanut butter, right? And so now, with our words from before, our work in earlier sections and discussions, that and turns into a multiplication. This is that product rule for probabilities. That and, that intersection, we want all 3 of these to happen at once. And so we multiply, and then from our work above was the probability that they prefer chunky peanut butter. That was at 0.46. I'm gonna put it in red. My apologies there. Color coordinating, but that chunky peanut butter, 0.46, that 46%. And we're gonna multiply it by itself 3 times and raise it to the 3rd power. And so if I do that calculation, just type it in 0.46 times 0.46 times 0.446. Type that properly. Multiplying out of 0.46 to the 3rd power, we're getting this long decimal result, 0.097336. And again, rounding to 4 decimal places, 1, 2, 3, 4, right? Including that 0 is still taking up a place value. Looking to the right, that 3 says that the first 3 can stay the same. So my rounded value 0.0973. Right? So a low probability, not unusual yet. In terms of being unusual, if that probability is less than 0.05, less than 5%, that's when we start to say something's unusual. But there's our probability. So now this next one was a probability that when I randomly select 2 people, was the probability that both people, right, of those 2 prefer smooth peanut butter, okay? In that case, if we're going to randomly pick 2 people, we're seeing, okay, person 1, first person, prefers smooth. And later we can jump right to that multiplication that's going to go on like above, right? But, and the second person prefers smooth as well. Right? And so from our work here, the probability that the first person prefers smooth, 0.54, that 54%, and comes down as a multiplication. The second person preferring smooth peanut butter as well, because we're taking from a large population, that probability doesn't change. The same likelihood that my next person is going to prefer smooth peanut butter. And we do that multiplication, 0.54 times 0.54, right? That 0.54 squared. Doing that calculation, we're getting here 0.2916 is already 4 decimal places. There's no need to round. We can keep that entire decimal result like so. And so this next one kind of brings up something interesting, and also another phrase that we can possibly see by looking at this next one. What's the probability that when I randomly pick 3 people, okay, that exactly 2 of those people prefer chunky peanut butter, okay? So kind of building up, what we might start to see is that, okay, well, person 1 prefers chunky peanut butter, and right, we want 2 people out of that group to prefer chunky peanut butter as well. Okay. And that third person number 3, if we only want exactly 2, that this person prefers smooth. Right? So there's 2 people that prefer chunky peanut butter, exactly 2 out of the 3. This last person liking smooth, right? But when we go to pick people, we didn't specify for those 2 that it had to be the first 2, right? It could have been, like we can say now, or it could have been that person 1 prefers chunky, and the second person, now this middle person, person number 2, prefers the smooth. And again, we might kind of shorten our notation and use some other symbols, right? So reduce that writing, but really kind of thinking about how this organization can change. That person 3 prefers chunky, right? So now we have 2 people that prefer chunky, 1 person that prefers smooth out of that total 3. But then again, there could be, or that the first person prefers smooth, and then our second and third person both prefer the chunky peanut butter, right? The last 2 people are going to be the 2 that have that preference for chunky peanut butter. But in each of these possible outcomes of selecting 3 people, we have 2 people that prefer chunky peanut butter and 1 person that prefers smooth. And we can double check, we can see if there's any other way we can reorganize, right? If 4 people, might be more ways of rotating or cycling through these different options. But as we start to go through, right, those and we're going to take those individual probabilities, multiply together, and then that or, we're going to add those possible results. Okay? And so when we do that calculation, right, preferring chunky, that was that 0.46. Let's keep that up here, right? Prefer chunky, 0.46. Prefer smooth, that was that 0.54. And so if I start to multiply together, 0.46 times 0.46 times 0.54, we're getting this long decimal result. 0.114264. If I was to do the calculation again here, chunky 0.46, smooth 0.54, chunky again 0.46, right? Notice it's those same three values. Now all we've done, those same probabilities, right? All we're doing is changing that order that they're appearing. 0.46 times 0.54 times 0.46. We're of course going to get the same decimal response there. So you can imagine we'll get the same result when I do this last possible organization. We'll get the same product here. So let me jump ahead. And now, because we would be happy with any of those organizations, that OR statement, the OR translates into an addition. So we're going to be adding those three probabilities together, or taking and multiplying by 3, right? And as the end result, our probability of exactly 2, thinking about, well, dot, dot, dot for that preferred chunky, right? The long decimal, taking these values adding together, 0.342792, rounding that to 4 decimal places, 1, 2, 3, 4. That's 7 value we're rounding. 9 tells us to round up, 0.3428. Okay. So looking at that result, that rounding involved. And these are kind of common problems that we see that percentage being used to represent our probability from these large populations. And as they're making those selections, right, kind of multiplying that the first person has this characteristic and the second person also has the characteristic. Depending on how many people picking, right, continuing the multiplication. We have to be a little bit careful then. If the quantity we're looking for, those two people, have this characteristic out of a larger, then we might not need to think about that other ways of arranging. Okay. All right. And so then lastly, with this idea of making selections, when we have the percentages, right, that's commonly where we have a large population. But now it can also be the case where we're making some of these selections, picking from a smaller sample, a smaller group. I'm going to kind of make this a little bit bigger. There we go. Okay. And so now I'm looking at this next problem. A math club on campus has 25 members. Right. So now we have a smaller population, a smaller group. Of that 25, 14 are male students, 11 are female students. So now we're going to make this look. If one student is selected at random, find the probability that the student is a male, right? So in this case, we start to see these categories, right? So there's our total, there's our N. And then we have these smaller groups, right? The 14 male. And then the remaining total, right? If they didn't tell us how many were female, assuming we only have those two genders identified, our total 25 minus 14 gives us the other amount, right? Our 11 female. That other category. Again, depending on what we have, we might see multiple subcategories, okay? But when we start to work on this problem, so if one student is selected at random, find the probability that the student is a male. So like we had done in our first example, that two-way classification, the probability taken from this math club, that the probability that the student's a male, out of that total, 25 students, 14 are male, right? And if we do that division, 14 divided by 25, 0.6. And again, we could have worked on that decimal, but there's our result, right? Doing a quick division. So then if two students are selected without replacement, find that probability that both students are male. So now in this case, when we start to see that we're drawing without replacement, right? Now the denominator will get smaller, right? We're reducing the total to select from with each pick. With a larger population, like those percentage problems we just completed, I don't have to worry about that denominator change because we're dealing with such a large population. Taking one person out of a million is not going to make a big difference in my next selection. But now with these smaller groups, right, taking a smaller class size, okay, we have those kind of specifics, then definitely it's going to take a toll, it's going to make a difference when I make that first selection, whether it's a male or female. It's going to reduce the number, change that probability when you start to see this idea of having our events being independent or dependent, right? Depending on who I pick first is definitely going to alter the probability for my next selection, okay? And so as we start to go through, all right, the probability that person one is a male, right? Out of those 25 students, if the first students is a male, right? Before I pick anybody, there's all 14 males out of that group of 25. But now, our second person, male as well. So now, in my second selection, because we're making a selection from a smaller group, the sample, instead of having 25 people to pick from, now there's only 24 students. Imagine, right, in this club or in your class, we're making a selection from that group of 25. We have the first person pick come up to the front of class. Now, when I go to make the next selection, there's only 24 people sitting out there. If the first person is a male, now there's only 13 males left. So notice that both the denominator getting smaller, but also the numerator can change. Okay. And so in this case, seeing that reduction, we're going to use that and statement again. The first person is male and the second person also male. So it's going to return to a multiplication. And depending, right, we can work on with the multiplication, simplifying across, right? We can divide 14 and 24. We can divide those both by 2. They're both even and reduce, get a smaller fraction. Or we can multiply straight across the numerator, 14 times 13, 182. Multiply straight across the denominator, 25 times 24, 600. Okay, let me switch sides here so I don't bump it. There's our long fraction. Remember, multiplying, we just multiply straight across the numerator and denominator. Doing that division, 182 divided by 600. We get 0.303, all those threes repeated. Rounding to 4 decimal places. That 3 says those digits are the same, so 0.3033. All right, so about 30% chance, a third of those possible outcomes. So next up, if 3 students are selected with replacement, find the probability that all 3 students are female. So now, in this case, with replacement, doesn't happen very often, but we can start to see now. We go back to those original amounts. Right, those original totals for each selection. More commonly, we're going to see cases where we are drawing without replacement and needing to reduce those values. But in this case, we're looking for the probability that when we pick 3 students, all 3 are female. Okay. Again, we're going to do our multiplication. We have all 25 students to pick from. And so for our first student being a female, 11 out of the 25. But now instead of having that person stand out, now they're going to go back to their seat. And we're going to make that selection again. So we have, again, back to all 25. 11 female. And the last person as well, same ordeal. We're not replacing, or we are replacing, pardon me, we're not having that student stand out. So we are replacing them in the group each time. Also doing that multiplication across, right? With replacement there, those values, those fractions stay the same. 11 times 11 times 11, 1,331. 25 times 25 times 25, 15,000, pardon me, 625. If I take that division problem, type that in, 0.085184. We could have also done that 11 divided by 25 raised to the third power. Okay, and so our higher exponents on somebody's calculator, we gotta find. It's x to a power, which is above, what did we, where did it go? Oh, well, here, there it is. Raised to the third power. And notice that same long digit decimal, okay? And so if I round this to 4 decimal places, 1, 2, 3, 4, that 8 rounds the 1 up. So in this case, as a rounded result, 0.0852. Okay. And so then last problem here, if 3 students are selected at random, find the probability that at least one is a female, right? So in this case, this brings in an important phrasing when we're looking for the probability that at least one has whatever that characteristic is, in this case being a female. Instead of having to think about that cycling of different possible results, like we did with exactly 2 people that prefer chunky peanut butter out of the 3 that we're selecting, right? Now, at least one, right? Now there's a lot more options because we have 1 student as a female, or we have 2 students as a female, and again, in any order, the first and the third, first and second, second and third. So there's a lot of different variations that we can pick. And so instead of having to cycle through all those options when it's at least one, we can do this calculation, that complement work, 1 minus the probability, and the complement of having at least one is that we have none, right? None of the students have whatever that characteristic was. So in this case, if we're looking for the probability that we have at least one female out of that group of 3, we can translate this as 1 minus the probability, right, that none are female. Well, another way of wording that, right? So here's that kind of phrasing, or this is equivalent 1 minus the probability, right? That we have all 3 male, right? So thinking in the context of this particular problem, the fact that none are female means that all 3 of those people we're picking are male, okay? And so then as we start to calculate that, then the probability at least one female we're looking here, 1 minus, and now the probability of all 3 male, kind of like we talked about up here. And again, we'll assume we're drawing without replacement. That's our more common aspect here. We'll get 14 over the 25, then 13 out of 25, and lastly 12 out of 24. Sorry, just messed myself up there, right? Because now if I'm drawing without replacement, let me make this note up here. So we'll clean that up. I'm going to assume that once I make my first selection, we're reducing the amount we have to pick from. We start with 14 males total. If the first person I pick is a male, then there's only 13 left. If the second person I pick is a male as well, now there's only 12 left. And again, 25 students to start. After my first selection, 24 left. And my third selection, 23 people left, right? And so as we start to calculate, we can do the fraction work first. We can do 14 over 25 times 13 over 24. times 12 over 23. And again, there's other ways we can multiply across the numerator, multiply across the denominator, then simplify. Keeping track of order of operations here. We want to make sure we divide individually. Calculate there, right? And again, for this work, keeping all of our decimals only rounding at the very, very end is going to be a key strategy here. But for that portion, the probability of all three are male without replacement, 0.15826,087. And if I do that subtraction, 1 minus that long decimal, 0.15826,087, 0.84173913. There's that long decimal result. Finishing up finally, rounding to 4 decimal places. That probability that at least one student is a female out of those 3 students selected, 0.8417. Okay. And this would work even with our percent probably or picking with replacement. That same type of calculation is going to work. The big deal here with that probability of at least one, we're using that complement work to organize and rewrite. Okay. All right. So here's some of our common probability problems set up and computed right from that chapter 5 work dealing with those probabilities. Okay. So I'll leave this here for your review and hope that helps out in that understanding. All right. Take care, y'all.